All right, diving in today, folks, we're taking a deep look at something pretty fascinating. It's the Gemma 3 technical report, fresh out of Google DeepMind.
Yeah, hot off the press, right? You've shared some snippets from your notes back on March 25th, 2025. And of course, we've got the Gemma 3 report.pdf itself. So I think we're in a good spot to, really get a handle on the real academic meat of this thing, the novel engineering, the core contributions.
Yeah, absolutely. And I think, our goal today is to really zero in on those innovations. Like what really sets Gemma 3 apart? What's groundbreaking here? And, try to paint a picture for everyone listening about what makes this such a big step forward for open language models.
I think that's a great way to put it. It's not just about like bigger is better, right? We're talking about more intelligent approaches, like from the ground up.
So, Gemma 3, I guess starting from the basics, like what's the fundamental idea? What are they building on here?
Well, so I mean, at its core, Gemma 3 is the latest iteration in the Gemma family, right? But what's really interesting from an academic perspective is the fact that it's co-designed with Google's Gemini models, the really high performance ones, and that suggests a pretty deliberate transfer of insights, maybe even architectural strategies from that cutting edge research into this more accessible open framework.
Right. And, there's all this talk about it being lightweight, but also very capable. So, like, how do they strike that balance?
You hit the nail on the head. I mean, the report really emphasizes that even though, it's got this relatively smaller parameter count, right? We're talking like 1 billion to 27 billion. Um, Gemma 3 can still go toe to toe with much larger models, at least in, a number of different evaluations. And this efficiency, that's a huge point of interest, academically speaking.
Makes sense. Okay, so then let's get specific. What are the really novel capabilities that Gemma brings to the table? Like, what new research avenues did they explore?
All right, so there are three main areas that I think really stand out, at least, from an academic point of view. First off, we've got native multimodality. So the model's ability to like really process and reason about both visual and textual data, like right from the get-go.
So it's not just text anymore.
No, not at all. And secondly, they've got this significantly expanded context window. It goes all the way up to 128,000 tokens for the larger models, and even the 1 billion parameter version. That one supports 32,000 tokens.
Wow, that's a huge hop.
It is, and then finally, they've really zeroed in on broader language coverage. So, advancements in multilingual understanding and generation, that kind of thing.
Yeah, and that jump in context length, that's a game changer, right? I mean, from a research standpoint, we know how crucial that is for anything that requires like really deep reasoning over a lot of information.
Oh, absolutely. And the real challenge academically isn't just, making the context bigger. It's doing it without, blowing up the computational costs or making the performance worse on shorter sequences. So the Gemma team, they really aim to, at least maintain the performance of Gemma 2 or even improve on it, which is, it's no small feat.
Right. And I think it would be really valuable to delve into the multimodality piece a bit more. So technically, how do they go about architecting this visual understanding?
Right. Well, the real innovation there is how they integrated this specially tailored SigLIP vision encoder.
SigLIP. Okay.
Yeah. So this is a vision transformer architecture, a type of neural network that's particularly good at image processing, and it's got around 400 million parameters.
So it's a substantial component.
It is, and it's trained using a variant of the clip loss function.
Ah, clip. So this encoder has basically learned to align visual and textual representations.
Exactly. So the whole clip framework and by extension SigLIP is great at creating embeddings. Those are like, numerical representations of images and text. And the key is they're close to each other in this shared embedding space if they're semantically related. So basically this lets the model understand how, what it sees connects to what it reads.
That's amazing. And so how do these visual embeddings actually get incorporated into the language model's processing flow? Like how does it all work together?
Okay, so images, they get transformed into this sequence of soft tokens. Think of it this way. Instead of dealing with like raw pixels directly, the SigLIP encoder kind of distills the key visual information into a fixed number of vectors, 256 of them to be exact.
Okay, so it's boiling it down to the essentials.
Right, and these vectors, they act as input tokens that the language model can then, work with in the same way it handles text tokens. So this abstraction, it's really crucial for, managing the computational load of all this multimodal processing.
Yeah, it's like translating images into the language of the model.
That's a great way to put it. And then, you mentioned earlier this tech for handling, all sorts of different image resolutions.
Oh, right, right.
Their pan and scan method, or PNS. This is particularly cool from a research standpoint. It's inspired by the Elevea model, and it provides this really flexible way of dealing with images that, maybe aren't square or have super high resolution. And this all happens during inference.
Pan and scan. So how does that actually work? Like conceptually?
Imagine you've got this fixed size window and you're sliding it across a larger image. So the PNS method, it basically does that. It segments the image into smaller crops, all the same size. And then each of those crops, it gets resized to, the standard input resolution for the vision encoder and then processed.
Okay, so it's looking at the image piece by piece.
Yeah, and by processing these overlapping views, the model can actually gather information from the whole image without being limited by, the encoder's fixed input size. This helps avoid those weird artifacts or loss of detail that you might get with, just resizing the whole image, especially for things like, trying to read text that's embedded in the image.
So it's a way to maintain high fidelity, even with all these different visual inputs. And it's all happening at the different stage, which is computationally smart.
Exactly.
Okay, so let's talk about this massive 128K context window. How on earth did they overcome the well-known challenges of scaling context length like that? Especially that KV cache issue.
Right. So this is a big one, a really key architectural innovation with huge academic implications. Their main strategy is this interleaving of local and global self-attention layers. So for every one global self-attention layer in a transformer block, there are five lower ones. And the important thing here is that those local layers, they only attend to a pretty short span of tokens, like 1024.
So most of the computation is happening on this local level.
Exactly. So the really heavy lifting, the attending to the entire 128,000 token context, that's mainly handled by those sparser global attention layers. And this really cuts down on the memory footprint that's, normally associated with the KV cache, which in standard transformer architectures, that thing grows quadratically with the sequence length.
Right. So it's like a divide and conquer strategy.
In a way, yeah. And then they also made some tweaks to the rotary position embeddings, rope.
Right. You mentioned those earlier.
Yeah. So to make those global layers even better at handling this extended context, they bumped up the rope base frequency from 10,000 to 1,000,000.
And just to remind everyone, rope is that's how they encode the positional information of the tokens.
Exactly. So by adjusting this frequency in those global layers, the model can better tell the difference between the positions of tokens, even across these really long sequences. It helps avoid problems with the positional signal kind of fading out over long distances. Now, the local layers, since they're only dealing with shorter context, those keep the original base frequency of 10,000.
Okay, so different parts of the network are handling positional information at different scales.
That's it. It's all tailored to them specific context window. And then to stretch the reach of that global self-attention even further, beyond what they saw in training, they adapted this technique called positional interpolation. It's based on research by Chen et al. Back in 2023. And this basically lets the model generalize its understanding of token positions to these much longer sequences.
Wow. So it's like they're not just throwing a bigger context window at it. They're really carefully engineering how the model does it.
Oh yeah, it's a very sophisticated approach.
Were there any other architectural changes worth noting?
Yeah, actually. So they stuck with grouped query attention, or GQA, which is known to, make the attention mechanism more efficient during inference. It lets multiple query heads share the same key and value heads. And they also ditched the soft capping mechanism they used in Gemma 2, replacing it with QK norm, which is this normalization technique applied to the query and key matrices. This change, it was inspired by some recent work, and it likely helps stabilize attention dynamics and potentially improve performance.
So a lot of fine tuning out of the.
Yeah, definitely.
So that covers the architectural side. Now let's talk about the training process itself. Were there any particularly innovative methodologies used there?
Okay, so the basic pre-training recipe, it's similar to Gemma 2, but a key difference is this this much larger token budget they're working with. So for example, the 27 billion parameter model that was trained on a whopping 14 trillion tokens of data. That massive scale, that's a big factor in how well it performs.
14 trillion. That's an order of magnitude increase in training data.
It is, yeah. And this expanded data set, it includes the new multimodal data we talked about and a much bigger emphasis on multilingual data to, beast that language coverage. They've also got this refined strategy for making sure the languages are all represented fairly in the training mix. It's based on work by Chung et al. From 2023, and this prevents the model from being, too biased towards high resource languages like English.
Right, because just throwing more multilingual data at the problem wouldn't be enough. You need to curate it properly.
Exactly. And then, when it comes to tokenizing all that data, Gemma 3 uses the Gemini 2.0 sentence piece tokenizer, which has got this huge vocabulary size of 262,000 tokens.
So a much wider range of building blocks for the model to work with.
Right. And this tokenizer is designed to be, more efficient and handle a wider range of languages. And on top of that, they've incorporated a quality reweighing step in the data selection process. It's inspired by research from Sakdeva et al. 2024. And basically, this technique tries to, lessen the influence of any potentially low quality data points during training.
Okay, so they're not just scaling the data, they're actively trying to improve its quality.
Yeah, exactly.
And I'm assuming knowledge distillation is still a core part of their training strategy.
Oh, absolutely. Consistent with, the whole Gemma philosophy. All the Gemma 3 models, they benefit from knowledge distillation. So, that's where you train a smaller student model to basically mimic the outputs of a larger, more capable teacher model. It's a great way to transfer knowledge and smaller models punch above their weight, so to speak.
Okay, so that gets us through the initial pre-training. Now, the report talks about this novel post-training recipe. What are the key academic innovations in that phase?
Right. So post-training, that's where they fine-tune those pre-trained models for specific tasks. And, they really start integrating the new multimodal and long context capabilities. They focused on, things like improving the model's abilities in math, reasoning, chat, instruction following, and multilingual understanding.
And does knowledge distillation play a role in this stage?
For sure. They use an improved knowledge distillation process here, learning from a large instruction-tuned teacher model. They also use reinforcement learning, brain tuning, using enhanced versions of their bond, warm, and warp frameworks. And all of this, it helps align the model's behavior with, what we want to see. Things like helpfulness and safety.
And anything noteworthy about the reward functions they're using in this RL fine-tuning?
Yeah, actually, they're using a really diverse set of reward signals. This includes some, weight averaged reward models that are trained on human feedback. And then they've got code execution feedback, or RLEF, to make the model better at coding by actually checking if the code it generates, actually works. And they even use ground truth rewards for math problems, drawing on methodologies from DeepSeek AI and Lambert et al.
So they're pulling from a lot of different sources to make sure the model is getting the right feedback.
Right, and this multifaceted approach to rewards, it lets them target improvements across all these different capabilities.
Okay, so it sounds like a very rigorous approach. And I'm assuming data filtering is still crucial at this stage, right? To ensure safety and quality.
Absolutely, they really emphasize carefully filtering that post-training data to get rid of any personal information, any potentially harmful outputs, or, any other undesirable stuff. You really have to be meticulous at this stage if you want to deploy these models responsibly.
Right, can't just let it loose on the...
No, definitely not.
Okay. Now, the report also goes into some detail about quantization-aware training. So, what's the academic motivation there? What's the significance?
Right, so quantization-aware training, or QAT, is a fine-tuning technique. And it's specifically designed to create what we call quantized versions of the models. So basically, that means reducing the precision of the model's weights, like down to Int4 or FP8, for example.
And what's the advantage of that?
Well, it significantly reduces the memory footprint. And that means more efficient inference, especially on, hardware that's a bit more limited. From an academic perspective, QAT is all about exploring the trade-offs between, model size, computational efficiency, and task performance.
So they're thinking about how to make these powerful models more practical, more deployable.
Exactly. The report actually gives some data on the memory savings you get with quantitation at a 32K context size, just to highlight the real world bits of this research.
That's great because making these models more accessible is really important for broader adoption. Now, what about the compute infrastructure? Like, what did it take to train Gemma 3?
Yeah, well, training at this scale, it takes a lot of horsepower. They used Google's, advanced TPU infrastructure, so TPU v4, TPU v5e, and TPU v5p, and everything was super optimized to keep the training time down to a minimum.
So they were really pushing the limits of what's possible.
They were, and one interesting thing they did was they pre-computed the vision embeddings for the multimodal training, and that really cut down on the computational costs for the language model training itself.
Smart move. So pre-computing those features saved them a lot of time and resources.
Yeah, definitely. And then, of course, they use all sorts of sophisticated distributed training techniques like 0-3 for sharding the optimizer states across multiple devices, pathways for handling multi-pod training, and then they use the JAX programming framework with the GSPMD partitioner and the XLA
A
compiler.
lot of acronyms there. But basically, they're using all the latest and greatest tools for distributed machine learning.
Exactly. It's the only way to train models of this size effectively.
Okay, so we've covered the architecture, we've talked about the training process. What do the evaluation results tell us? Like, how successful were these approaches?
Well, the evaluation highlights are pretty impressive, academically speaking. The Gemma 3 27B instruction-tuned model, it actually performed really well in the LMSY chatbot arena, even when you compare it to, much larger proprietary models.
So it can hold its own against the big guys.
Yeah, which suggests that their architectural and training innovations really paid off in terms of real-world conversational ability. And then on those standard benchmarks like MMLU for general knowledge, Live Code Bench for code generation, and MAH for mathematical reasoning, Gemma 3 also shows really strong, especially compared to earlier Gemma models and even the Gemini family. Although the report rightly points out that, direct comparisons with externally reported results, those can be tricky because of variations in the evaluation procedures.
Makes sense. You always have to be careful about comparing apples to oranges.
Right.
Now, were there any specific ablation studies that they did that, that gave some insights into the impact of certain architectural choices?
Yeah, they did a few, and they offer some really valuable insights. So, for example, when they looked at the ratio of local to global attention layers and the size of that sliding window we talked about in the local attention mechanism, they found that even big changes to layers didn't really affect the perplexity much.
So that suggests that the configuration they settled on is a pretty good balance between efficiency and performance.
Exactly. It's a key finding for anyone trying to optimize, transformer architectures. And then they also showed that they could successfully scale the context length to that 128K using their rope rescaling technique. So that provides real evidence that the model can actually use that extended context for relevant tasks.
That's good to see. And what about the multimodal capabilities? How did they evaluate those?
So their evaluation showed that using higher resolution vision encoders generally leads to better performance on tasks that, require visual understanding. And their ablation studies on pan and scan method, those clearly showed how effective it is for handling images with, all sorts of different aspect ratios. And for tasks that involve reasoning about visual information that's spread across the whole image.
Okay, so that added complexity of multimodality is it's really paying off.
It seems like it.
Now, one area of ongoing research in LLMs is this whole issue of memorization of the training data. So how does Gemma 3 fare in that regard?
Interesting. The report says that Gemma 3 models actually have a significantly lower memorization rate compared to previous Gemma and Gemini models. And they figured this out using some pretty rigorous methods to detect both exact and near duplicate matches to the training data. And on top of that, their analysis didn't find any instances of personal information being memorized, which is really important for privacy and, responsible AI development.
Yeah, that's definitely a good sign. So it sounds like they're making progress on that front.
They are.
Now, in terms of responsible AI development, what kind of measures do they take for safety and security?
While responsibility, safety, security clearly top priorities throughout the whole development process, they implemented, internal safety protocols that are in line with Google AI's overall safety guidelines, and that includes, governance and risk assessments specifically tailored to the unique challenges of multimodal LLMs, and of course the fine-tuned models. Those are all aligned with Google's established safety policies.
Okay, and did they implement any specific safety mitigations during the training process itself?
Yeah, they did. So they filtered the pre-training data for safety, and they used both supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF, to steer the fine-tuned models away from generating harmful or inappropriate content. And then they did some baseline evaluations using what they call adversarial prompts, and those showed a really low rate of safety policy violations.
So they're really trying to be proactive about safety.
Yeah, it's not an afterthought. And then they also did sections of the model's knowledge in some pretty specific and potentially sensitive areas like chemical, biological, radiological, and nuclear materials, using specific knowledge-based questions. And their findings suggest that Gemma 3 models don't really have much expertise in those highly sensitive areas.
Okay, so they're thinking about potential risks across a whole range of different concerns.
Exactly. They're really emphasizing this holistic system level approach to making sure that Gemma 3 is used safely, responsibly. And they acknowledge that, this requires ongoing effort and and adapting to specific use cases.
Well, this has been an incredibly deep dive into the Gemma 3 technical report. I think we've covered a lot of ground. But, as we wrap up, what are the key academic takeaways that you think our listeners should really remember?
I think the core contributions here are really in a few key areas. First, the architecture itself, the way they designed it to handle that super long context and to seamlessly integrate multimodality, that's really innovative. And then, of course, there's the training and post-training methods. They're using knowledge distillation and reinforcement learning in some really sophisticated and effective ways. And then, you can't forget the performance itself. It's competitive across a whole range of benchmarks. And all of this is done with a really strong emphasis on safety and responsible development, including that notably lower memorization rate we talked about.
Right. And what about the bigger picture? How do these advancements impact the field of open language model research as a whole?
Well, I think Gemma 3 is a really strong example of what's possible. It shows that you can achieve state-of-the-art capabilities in open language models while also pushing for efficiency and accessibility. The architectural innovations for long context and multimodality and those refined training techniques, they provide a blueprint for future research and development. It's a path towards models that are, more capable, more versatile, and can be studied and used more widely by the research community.
Absolutely. So as we wrap up this deep dive, here's a final thought for everyone listening. Given all these advancements, what are the biggest open questions that are still out there, in our pursuit of truly robust, reliable, and beneficial AI? How might these innovations we've talked about today lead to breakthroughs in your own work or your areas of interest? It's a fascinating time to be thinking about these things. So thanks for joining us for this in-depth look at Gemma 3.
It's been a pleasure.